In this video, we'll learn how to create emission and excitation spectra for a fluorescence data. Here is the file that you got from the fluorescence computer. You named it as quantum.emission spectra, and this is a text document. That means you cannot open this document directly in an Excel file, but you can go to Excel file and open this from there. Like you can right click and create a new Excel file. I created one that's here. It's a new Excel file and I named it as quantum.emission and excitation. And you open that, it's a blank new Excel file. From this, you can go to File, Open, find the file that you got from the fluorescence computer. Here in this folder we have the file that you downloaded from the fluorescence computer, but we don't see it because we have to change the search for all files. Okay, so when you change this from all Excel files to all files, you'll see your text document, right? So here is the document that you sent me. We hit open, and now we have to convert the text document into Excel document by selecting the delimited and click next, and finish. Okay, here's what you got from the computer, right? And you're right that we have a mirror image, or we have a repetition of the data, and this is something that that I don't understand. Probably we need to explore what the data in the bottom means. It looks like it says excitation correction, but I don't know what was corrected, and the numbers are very low. It's usually less than 0, so I think it doesn't affect our spectrum much. So I'm going to delete all of these. Whatever is in the bottom, I'm going to delete them. Right? So select all these rows and hit delete, and I'll just keep whatever is in the top. Right? Okay. Right. I don't want any of these information. Okay, I don't know what these numbers mean. So let me delete those numbers. I don't know what these numbers are. Okay, let me delete that too. Okay. So delete these rows. Now you see that here is a wavelength and here is the absorbance. Wavelength, absorbance, wavelength, absorbance. X-axis and y-axis. X-axis, y-axis. Right. We don't want the x and y, so let's delete that row. Okay. Here's a wavelength and absorbance. Now to create to plot a chart that contains all the emission and all the excitation, we need to change something here. All right. Let's try to create two graphs. One is for emission, one is for excitation. In the emission graph, we put all the emission data. In the excitation graph, we put all the excitation data. Like there are 5 or 6 excitation graphs that we combine in a one graph. In emission graph, we combine all 5 or 6 emission, all 5 or 6 samples. Okay, for that we need to create one single y-axis, sorry, x-axis, the wavelength axis. So I'm going to create it's an insert. Okay, there's an insert, and then starting from 300 is the lowest wavelength we got so far. So from 300 to 700 is the highest, right? So we want to we want to create a y-axis from 300 to 700, and if you see this, since we gave the size 2, it increases by 2, right? Scan size 2, right? So let's start from 300 and 302 and 304 and go up to 700. I think you can just drag it, right? It increases. So let's go all the way to 700. Still 500. Okay, here's our 700. Okay, let's keep it that way. So 300, 302, 304, 306. Now I want to copy this baseline. Is this a blank? Yeah, we don't want the blank, right? We don't want the blank. So I'm going to delete these. Right. Now this is for 40 seconds quantum dot. So I'm going to copy this title and paste it here. 40 seconds quantum dot. And so we start from 535. We started our scan, the emission scan, from 535. So I'm going to copy these and paste it near 535. Do we have 535? Looks like we don't have 535 because these are even numbers. So let me paste at 534. So one wavelength, 1 nanometer doesn't change much. Okay. What is this? This is 40 seconds quantum dot. We scanned from 535 to 699. So you see that 534 or 535 to 699 or 698, right? Okay. Now we don't want these two columns. Let's delete these two. Okay. And this is emission, right? So sorry, this is excitation. Let's come back to the excitation later. Let's go to emission now. Okay, this is 60-second emission. So I'm going to copy this title and paste it here. Probably need to insert some column. Insert. Okay. Okay, 60 seconds. And we scanned our emission spectrum from 432 to 700. So I'm going to copy the absorbance and paste it from 432. Okay, now where is 432 here? Here's our 432. So I'm going to paste the data here, and that is 60 seconds quantum dot emission. Now we don't want these two, we already copied that. Let's delete those two columns. Okay, this is excitation. Let's come back to excitation later. This is 80 seconds excitation and 80 seconds emission. We want the emission, right? Let's copy this title and paste it here. And you see that we started our scan from 544. So I'm going to copy that, copy the absorbance or emission, and paste it at 544. Where is 544 here? Here is our 544. Paste it here. Okay, that's our 80 seconds emission. We're done with 40, 60 and 80. We're done with that. Let me insert some more columns. Okay, so we're done with 80 emission. These two columns are done, so I'm going to delete those two columns. And here's 100 seconds sample. We started our scan from 432 and copy the emission which is the y-axis value, and paste it at 432 here. Where is 432? Oh, we have to copy the title first. Let's copy the title and paste it here, and copy the emission and paste it at 432. Okay, there. That's 100 seconds sample. We're done with the 100-second emission, so let's delete that. Okay, like that, you can copy paste 120, 140, 160, and 180. Right, I'm gonna pause the video and do all the remaining cut and paste, and then resume the video in a few minutes. Okay, so here I cut and paste all the emission data. Here is a 20 seconds sample, 40 seconds, 60, 80, 100, 120, 140, 160, 180, 200 samples. And most of the samples started from 432. That's where you started your scanning range. And most of them end at 700, right? So we don't want anything below that. Let's delete those things. Now let's create a graph for the emission spectra. Okay, select an empty cell. Right? Select an empty cell, or I think you can just select the data range. Right? Select the data range. Okay, select the range from first row until you cover all the data, and go to insert, go to all types of chart, and then scatter. In the scatter, select the line. Right, so yeah, that's right. That's the graph we want. That's it. Okay. Okay, so here is our quantum dots emission spectra. And you can always adjust the size of the graph. Like you can enlarge the graph and select the y-axis range. Right click, sorry, x-axis range. Right click the x-axis, go to format axis, and then change the minimum, which is, let's say, 400, and then maximum could be 700. Hit enter. Right, and then you can move these labels to the right side. For that, you can go to here, legends, to the right side. Right. You can literally move them and extend your chart. Okay, you can create a title, emission spectra of different size, quantum dot CDSE, quantum dot samples. What solvent? In ODE, octadecene solvent. Emission spectra of different size, quantum dot in octadecene solvent. Okay, again, we had a blank of octadecene, but we didn't subtract it. We may subtract it later, but now this is how you do the emission spectra. And you can compare the lambda max here For the 20-second sample, the lambda max is here, around, let's say, around 518. And for 40 seconds, the lambda max is around 538. For 60 seconds, the lambda max is 546. For 80 seconds, the lambda max is 550. So it's a wonderful data. You got it. Because when the size of the quantum dot increases, the lambda max should go right towards the red region, right? So size of the quantum dots and the lambda max are directly proportional. If the size increases, the lambda max should redshift. That's what you got. We probably need to normalize that. Normalize these lambda maxes so we can compare that. It's a different story. Normalization means don't worry about the y-axis. Bring all the absorbance to one range, like a same height. Bring all the peaks to same height. It's just a mathematical formula. You can apply that on the Excel sheet, and so here you can see that this is shorter peak, this is a taller peak, and these are in between peaks. You can bring them to a single height so you can easily compare the x-axis value, right? I'll do that in a next video, but for now, this is how you create emission spectra. Use the same method to create excitation spectra and post it on your OneNote, right? That's a task for you.